Like, you know this. I'm like, I do.
Okay.
I do know this.
Courtney, it kind of looks like you're wearing PJs.
This is a pajama shirt. I love that. From Maybe.
Wow.
Yeah, 2XL.
Anything is a PJ shirt.
It's on sale.
Sleep there.
Sleep it, yeah.
If I wear jeans.
Even jeans.
Oh my goodness.
My sister's boyfriend wears jeans to bed. And it makes him sweat. How many?
So few days, not so many.
Yeah, that is
So few days.
Wait, how many weeks do we have to like?
Yeah,
You have an eyelash on your glasses.
That's probably a lame.
Yeah, what is it?
I think it is main subject to discuss right now.
12. Final.
Okay.
At the time, 12 o'clock. What?
I think would be right. 12.
Yes.
Unfortunately, we are not in the year
Yeah.
2012.
Oh, man. That was a good year.
Did I even import this?
I was still in middle school. I had a blast in middle school.
Oh, me too, peaked. I peaked.
I peaked in
hard.
middle
My parents divorced in middle
Well,
school.
mine too, and I also went to Catholic school, but. Me in middle school.
Wait, we have class on Monday,
This Monday?
upcoming Monday.
Yes, of course.
I will be attending that class via Zoom.
That's fine.
Yeah.
Apparently, we're like super far behind in Inord, and we don't have class. We didn't have class today because parents were in town for something, and we just decided to call off class on Friday, like for
So there.
like okay, well, surely we're not that far behind. Yeah,
This was good.
I don't know.
I feel like.
I didn't check really.
What? This is
You know,
actually-
as a class, parents
Huh?
decided.
The teacher,
Yeah, they could just.
Uh,
Well, it is today, tomorrow, and Friday.
he's
So.
Today, tomorrow.
Okay, what's on the docket for today? What's on the docket?
On what?
On the
I
docket.
don't know what that means.
Like the
either.
list of things to do and talk about.
The.
My presentation last night.
How do you abbreviate it?
Docket.
Docket, it's a legal term, for
Like-
judges.
On
It's
the
the,
agenda.
like the number of cases that they have to go through.
Absolutely insane.
I learned so much from you guys. I also learned, I didn't remember, but I learned how to say our feelings about Fred.
What are our feelings about?
You mentioned that.
You love Fred?
It was more like advanced things. I watch recordings for your words.
this.
Only positive things.
Anxiety of absence.
Huh?
Anxiety of absence.
There's separation plan.
I'm sorry for putting you through it.
Fred, are you planning to retransmit or work that was done Monday? Or it was the reason why you didn't came?
Someone's name.
It was part of the reason. Other stuff, I will get it into you today.
Okay, so you have good intentions.
Yes.
Thank you.
Only negative
Everyone
intentions.
finger hearts for Fred. You need, no, Sam, he needs the support.
Thanks.
Sending you finger hearts, Fred.
Finger hearts.
Okay, anyway,
I learned continuously.
the Korean thing
Korean?
comes from Korean pop idols.
Oh, interesting. They have many things. Is it heart upside down?
This, no, this is
Oh,
Delta,
Delta, okay.
to begin.
I do not want to begin.
Okay.
Well, then let's keep talking. What was your night last night?
Like 40 minutes of class.
So, I always, when planning classes, I always forget about holidays and miss count, but,
Oh,
so Thanksgiving takes away like 2 classes in 1 week, right? I especially miss the labs because it was time for projects. But probably, so here is the plan what we can do in the remaining part of the class. So, today I hope to finish Oscillator. Then we and I I already told that I feel sorry, but you accepted it. That we have escalating amount of materials, like 70% of materials in the last 30% of time, and then maybe well, I wouldn't say 90% of materials in the 10% of time, but it's getting a little more and more. So rotations, two-dimensional rotations and three-dimensional rotations, which is important because some molecules rotate. And when you take in second part of PChem from Professor Hamburger, research is related to rotational vibrational spectroscopy, and probably will cover it because it is more appropriate for statistical method. But you will get prepared. Also, this today we will see how the expectation value of position and momentum, not only necessarily in specific coordinate system, if you have X and P, the expectation values will perform rotations, right? Because it's two dimensions, and then one can define rotation. Like oscillator oscillates, but in specific degrees of freedom between the rotation. And it will be a smooth transition towards rotational degrees of freedom, which have to be here in this class. Rotations. Then in Monday, right? Today is Wednesday, then this Friday. So soon, two-dimensional rotation. And on I cannot imagine. On Monday, we will have three-dimensional rotations, which are more complicated, and we will have concept of angular momentum. Did you hear about it?
Yeah.
Really?
Yeah.
You're my
Angular
serious.
momentum?
Angular momentum.
Yeah,
In which?
in trig and
I
physics.
was gonna say, we also learned about it in others class. Yeah. We learned about angular momentum, but not like, it was more of identifying like, it was like quantum numbers. This is what it was involved with. We didn't actually do any mathematical, like,
I'm honored to be in the same room with highly educated people. Excellent.
I only know that because I've been tutoring 150. That's
Okay.
what we got.
And today, okay, whatever time left, we will revisit some things like this, right?
Yeah.
Computation between weather operators. And on Monday, we will have rotation operators around different axes, right? And then we look for their commutation. So when I was starting like my undergraduate times, it was a part that I hated a lot, at most. But it's a part of the class. I'll try to make this right smooth and quick so that you can easily forget it.
Okay.
Then after and yeah, why there are 2 Mondays?
Because that's a week
It's
later.
Thanksgiving.
Oh, okay. I was typing it myself an hour ago, but I already forgotten what it is. And then applications of rotation for raw vibrational spectra to help your future interactions with Professor Kerber, and SPD orbitals, which you know from your freshman time. And then Wednesday we will look on hydrogen atom. Some people think that hydrogen atom is the center of modern science and technology. One should spend the whole year on hydrogen atom, but you'll spend only 1 million.
Okay.
Then in December, we will have spin operators. I'm not asking because you are aware of spin, right? NMR, EPR, and for spin, you see here is the connection, wonderful connection that I never mentioned before, but here are rotations. And rotations are also in for rotating molecules. Here are commutations. Commutations will be for angular momentum. And when we go to spin projections like magnetization in the SX, SY, SZ direction, they will follow very similar commutation relations as for angular momentum. So you see, it's like a long story, everything is connected. Like oscillator, rotations, angular momentum and then spin. And then basic foundation level things will be done. And here is a really advanced topic that is never included in undergraduate classes, but many of you may need it for interpreting your wet chemistry lab. So in here we will have rotational vibrational spectrum when rotations and vibrations cooperate together. And in transpondent, it is when electronic and vibrational degrees of freedom also cooperate and give special observables for the spectrum. So it's amazing subject. I love it. And it is like top point in our academic studies. So everything we do, we'll be accumulating background to get through this material. Then there will be 2 meetings more on December 7th. I know you all are literate and you're more literate than myself. I'm not going to teach you how to write. I'm teaching how I understand it, how to write it. And you will compare like what are requirements for projects written reports.
So like what you want to see on the project?
Exactly.
Okay.
Okay. So
Yes.
do not take this title as an arrogance telling like
Learn how to write.
okay. Then on the I think it is that week manuscripts at least 4 or more pages are due.
More than 4 pages? Okay.
Um,
4 slides.
no. You for the projects, you do it for the exams. So, written reports. You see what Sam is browsing.
Oh, yeah.
Okay, so here is the thing. When you are projecting your like plans, intentions, personalities to this project, you think, I want to get rid of it. I want to make as minimal amount of effort. I want to have it completed and have as brief, as short as possible. But by human nature, as soon as you start writing, even if you never plan to be brief, you will get so excited and it will be difficult to stop you. So you see from this, so everyone writes for like 10 pages. Although like I'm fine with 4.
At least 4.
At least 4, yes.
Okay.
My magnum opus.
It's
was
31
pages.
Your what?
magic of creativity. As soon as we go away from like memorizing and learning like dedicated amount and you do something with your own interest, creativity skill launches and it's difficult to stop it. And it happens. And then the final draft. Oh, okay. I haven't. So what does it mean peer review?
You look for each other's stuff.
I read it, full criticism,
We
nice notes, draw a little like
Give each
dinos.
other
and kind of
questions and
Like the homework,
trash each other's
but
writing.
better.
exactly.
Yeah.
So it is like we will like I know collect, distribute, you write feedback, and maybe there will be some guest editors, and then during the weekend you will look through feedback and make another iteration. You will improve your works because you'll see, oh, my work is so beautiful, I'm proud of it. And then we didn't define this, the line is ugly, and you can quickly improve things, right? And then on Monday, final manuscript is due, and then sometimes during the week, I prefer Thursday, 12. But
I think we have
The schedule is on one of the next few slides, the final schedule.
We do have a set.
I need you to teach me. I don't know how to read this crazy table.
I think it's my Thursday.
Wednesday at 8. Oh, wait, no.
we have an 8 a.m. final.
So.
Oh. I thought that was the Diffie Q final. It is.
No, it's not. It's at 3:30 p.m. on Thursday.
Yeah,
So
so
we're
relax.
3:30 to 5:30.
Let's see.
It's in Maria's syllabus.
Monday, Wednesday,
Tell 'em.
Friday.
So
Well,
if,
yeah.
like Thursdays, I would prefer it, but I think we can, have some, like,
But it's at 8.
late classes can have finals late at night. Our lab is part of our class, so we can just do the same time when the lab is.
On Wednesday?
Yeah, but we'll come to conclusion and find a way that will make everyone happy.
Okay.
Okay, so I'm not insisting, probably the later the better, so you have more time to prepare. And maybe if it is not on Wednesday, that on Wednesday we can meet for the last time in the lab to like tie the loose ends. Do things like this, but if you want. Okay,
Okay.
sounds like a plan.
Sounds like a plan.
Okay. Here are your projects. We are not talking about them right now to save time.
For right now, it's
Uh,
we get closer if we want to move it to Wednesday.
In previous years, some people were selecting two-dimensional rotations and two-dimensional hydrogen atom and were generating this analog of d orbitals. Oh, it moves. I have to learn about it.
Wait, Dimitri, just to clarify, so as of right now, we're gonna have our presentations on Thursday at 11 a.m. But as we get closer, if we want to change it to Wednesday, we can.
Absolutely. I do not have any room reserved. It's only my personal wish.
Okay.
I like Thursdays. Because Friday is already like weekend, Wednesday is still a working weekend, Thursday is like,
Thursday, it's like almost the weekend time. And so you're excited for the
little.
weekend,
Yeah.
but also everything's always due on Friday, so I'm still like, I have so much to do.
Yeah.
I think this figure was done by one of your class, not classmates, but previous year. And it is like two-dimensional rotations that we will cover, and it could be someone else.
Is that the 2D angular rotations of Warmoth or non-equilibrium formation?
Related, yes.
Of the semester.
Let's go, Joe.
Joseph.
Here,
What's we can do?
I guess.
Okay.
Stay here.
Is it what we got right last
Yes,
time?
yes.
You recognize it.
Yes, it's the Gaussian.
Did you watch Back to the Future?
No.
Yeah, I love Back to the Future.
It's a movie.
Flux capacitor fluctuates.
Yeah.
So here oscillator oscillates. I think I have the slides just in case if you would miss to deliver it last time, but we did it, right? So here is a little summary of the whole, not the whole class, of what we did up to now. And one axis is methods, another axis is models, and we did so by talking to each of you from time to time, and especially Sam yesterday, I realized that I missed to clarify some things that you all understand, but if question comes unexpected, you spend time on figuring out. So there are methods and models, and it's very simple. You know it, but so methods and models are dramatically different philosophical concepts. Methods are protocols how we treat models, and models are analogs of different physical systems. Like if someone asks you which models you studied in this class, you do not mention like Schrödinger equation or Heisenberg equation. You mention electron in a free space, electron in box, like harmonic oscillator. And then we will have rotator, spin, and hydrogen atom. So models and methods are different things. And a plan of our class is like intersection of these two concepts. We apply different methods for different models. Right? So we did ladder operator for harmonic oscillator. What else we did? I cannot read my own things. Oh, coherent state for harmonic oscillator. And we do need to arrive to this picture. So we have plenty of time if we do not go to Blackboard and derive things. But just in case. So here is the last slide of our today's meeting. And how to interpret it if we skip all mathematical details and just interpret. Like another view on this class with physical chemistry is a skill of converting words into equations and equations into words. If you want to convert these equations into words, what is happening? So this is a solution for coupled motion of expectation values of position and momentum of a harmonic oscillator of mass m and frequency omega. This solution comes from a differential equation. They will come, and standard way to solve linear differential equations is to solve for selected initial condition for time equals 0, right? So in some sense, it is predicting a future, but not global future for wave function, but only a specific property of the future, where the center of the effective will be and which average velocity we will have, or average momentum. And this future can be presented from the past, from the values of these observables at the initial time. So here we can launch our human common sense and imagination. Suppose initially we have 0 momentum. If momentum is y-axis, then we are on the x-axis. And we have some elongation. So we extended the bond toward the positive direction, right? What should happen? Ball on a spring or just interatomic bond. If we do not write it to completely dissociate, it will tend to reconstruct back, right? So we elongated it, and then it tries to contract, right? But when it contracts, it picks up the momentum. Momentum will go into the opposite direction. If we extend it positive, the momentum will go backward. So negative momentum raises down, right? So we have this little arrow. So in average, we decrease position and increase negative momentum. And then we keep going, keep going. At some point, the bond will arrive to equilibrium distance, right? But at this time, due to inertia, it will pick up a momentum. And although it is literally above the 0 force point, above the equilibrium, this momentum tends to bring it to contraction regime when bond is shorter than it usually is. So position is equilibrium, momentum is so negative that it keeps pushing it backwards due to inertia. So we keep getting smaller and smaller bond distance. And because energy, kinetic energy of motion converts into potential energy of contracted bond, it resists, it exerts force. And momentum quenches and gets smaller and smaller. So momentum from negative gets back to 0. And then we are far in some negative value. Then now we have a big force that drives it back towards expanding the bond. And then bond starts to expand and momentum raises in positive direction. Right? So it raises to the maximum, bond comes to equilibrium, but now it picks up the speed so no one can stop it. Right? And it passes equilibrium position and goes further to elongation. And now momentum is still positive, but it becomes smaller and smaller and comes down to 0. And then the system arrives to where it started. And if our model is isolated, if we do not have dissipation mechanisms, then these oscillations will go on forever, right? Now, what I did show would work if momentum is 0 and this one is not 0. But if one starts anywhere, here as initial condition or there, it will still be the same trajectory. Like if the values are a little smaller, if you start there or there, it still will be rotations clockwise. So it's like swirl of all possible solutions. So all solutions will be circled. Okay, now I need to entertain you for another 15 minutes. Patricia, do you like it? Okay. And if it is two oscillators, then it will be four-dimensional trajectory. Right? Okay. I cannot read my own handwriting. Unfortunately, or more unfortunately. So expectation values are done. Let me stop recording and break over there, and then I will definitely entertain you. So,
Okay.
are we on recording?
It's at the top.
Yes. Paul. Review.
Dang, that's actually so cool.
So,
Jokes aside, that's so cool.
why Heisenberg left trace? What did he taught us? So that
Uncertainty.
uncertainty, and also he taught us that, come on, we do not need wave function. So we can do all quantum theory without wave function at all. So if we deal only with operators and matrix elements, then one can get the same predictions of the outcomes of experiments as through wave function. So when we follow the ideas of Schrödinger, we need to find wave function and then do this sandwich, bra, operator cat, and get expectation value. When we follow Heisenberg, we need only operator and Hamiltonian, and then we can predict what we already got in our answer for today's meeting, right? So what do we get forward?
Make sure what is a operator?
Any operator. Any operator, just general. Okay, so here's the little thing that we all agreed and decided before. So
Yes.
we do.
What?
Sorry, we're having an issue with the light coming out of these blinds. Watch your eyes.
Yeah,
I
it's
don't
gonna
wanna
be
get
bright
it.
for a second.
I'm okay.
Give flashbang.
Oh, there we go. See?
Yeah.
Yeah.
That's why they pay me the big bucks.
So here are our best friend creation and annihilation operators in direct notation, right?
Yes.
If we multiply a dagger A, instead of converting junior to senior or senior to junior, it keeps the same. We start from n+1 and we end at n+1, or we start from k and end with k, right? So number operator that was loved by Patricia. And we decided that it should be lower case n to avoid confusion with normalization. Okay. If we practice the same way how we derived number operator for different order, like when dagger goes first, it is normal order, and this, I don't know terminology, like abnormal.
Yeah.
And when we subtract them, the result will be unit operator. And if you want, we can prove it. So for one case, we get k+1, in another k, if we subtract, it will be only factor 1. So it will be a matrix with ones on the main diagonal, zeros everywhere. Unit operator. So it means it's a proof that if you do commutation of a dagger, the result will be unit operator. If you do a dagger A, it will be minus unit operator. Okay. I'm kind of jumping through and pushing it. We mumble most of the time and showing equations least of the time, but we will come to this logic, maybe not to this operators again and again in the remaining time. So for angular momentum and for spin, there will be similar style commutation relations similar chance to predict outcome without using wave function. So it is like Heisenberg view on quantum mechanics based on algebra of operators and commutation. Okay, now the Heisenberg equation of motion tells that time, we did it at the very beginning of the class, right? The time evolution of either operator or its expectation value is I over h bar commutation of the operator with Hamiltonian, right? So if you want to be abstract mathematical, we can remove this little Brian Katz. If you need actual expectation value, you just plug in Brian Katz and speak about equation of motion for expectation values. Hamiltonian for harmonic oscillator is number operator plus 1/2 and frequency, right? If you want absolute minimum of nodes that you inherit from this class kinetically, you can, it will be this equation. I encourage you to memorize a little bit more, but this is a minimum, right? Do not forget this one. Otherwise, I will be ashamed in front of Professor Carver. Now, if you want to practice Heisenberg equation of motion, we do need to perform commutation between Hamiltonian and annihilation operator if you want, if our A is A capital is equal to A lowercase. If you want to see how it sounds crazy, you want to see how operator changes in time. It's hard to tolerate. But mathematically, we have this number operator annihilation. I think it was one of the homeworks, right?
Yeah.
And then it is minus and if we see abnormal order of operators, we plug in the commutation relation, then things cancel, and we have -1 times A. I think you remember it from the homework. So by performing commutation between Hamiltonian and annihilation operator, we reproduce annihilation operator itself, right? This is a little mathematical wonder. Typically, one gets something very different. And same story for the creation operator. By performing commutation between Hamiltonian, it's only for harmonic oscillator. Therefore, it is unique and preferred toy of any theorist, because it has so pleasant commutations. One mumbles some general equations until let's apply it to something. Select harmonic oscillator and see how beautiful solutions are. So here one reproduces the operator itself. And we needed to practice Heisenberg equation of motion. Absolutely, yes, please.
I just want to clarify, when you have this. The operator sign that shows there's something is an operator.
Okay.
Yeah. Yeah, I wonder why for some you put it and for some you don't.
Because I'm lazy.
Okay.
So if one wants to be very rigorous, if one submits a paper for review to the journal, yes, one should put hat anytime it is operator and put either Brian Katz or just remove hat if it is observable or eigen, like Brian Katz if it is expectation value and no symbols if it is eigenvalue. Maybe this is some subscript. But now at least I have no conflict with myself. I understand what I need and just lazy to put another symbol. So no philosophical reason, only human laziness. Quite a presentation. Okay, now if we plug in operator A into Heisenberg equation of motion, so the h bar from here and h bar from commutation will cancel, right? And then
Yes.
you see that.
What's the expectation value you're thinking? That one is that was covered.
Same answer, laziness. Okay, Too much.
I think, some expectation. Oh, okay, I was thinking it's like.
So the equations will stay correct with or without this expectation value sign.
Yeah,
If-
I was thinking that was like, is it A?
This one is A, and this one is B. So we look for time derivative of annihilation operator. Okay, so H bar cancels, and then we see that change over time of annihilation operator is equal to annihilation operator itself, but with imaginary frequency omega. Here is one of the mathematical reasons why we suffered all this new concepts, because one doesn't need to solve complicated differential equations. If you wouldn't do these tricks, we will solve all problems as well. But then differential equations will be substantially more complicated, and we will waste time on boring math. Here, we just divide everything by A, multiply everything by dt, and you see this one will be log, right? This one will be linear time. And then we plug it into the power of exponential, like e to the power log A, e to the power minus I omega t. If we do need initial value, then it will be here. Right? You don't want me to prove anything, you accept it.
Yeah.
And it accumulates space, it oscillates complex space in the negative direction. If you do the same trick for the, oh, by the way, expectation value of annihilation operator, it at the same time is the mu or gamma that we used for coherent state, right? And we see that eigenvalue of annihilation operator is the expectation value of this annihilation operator, and it naturally rotates. So it agrees very well with coherent state being having oscillating nature. Okay. Now, if you do the same for creation operator, we will see that it reproduces itself, but sign is plus. We again solve this differential equation, and we see that it performs similar rotations, but in positive direction, right? Accumulate space. So for all of us, we are kind of departing from creation and annihilation operators, except Patricia. If you study a couple of oscillators and you continue the subject, it will be your alphabet. Everything will be done on language of all these operators. Now, here is the definition of how creation and annihilation operators are cast in as a linear combination of position and momentum, right? One can solve it back and express position and momentum as superposition of expectation values of creation and annihilation operators. But those A plus of t and A of t have been solved, right? And in certain specific cases, if initial A is not complex but real, we can put it outside of the brackets, and then we'll have summation of this exponential, right? Which is our old buddy, starts with letter E.
Euler.
Yes, Euler. So by adding together two exponentials rotating in the opposite direction can be replaced by cosine. If you do perform this transition carefully, right, one would include momentum as well, right? So because A dagger depends on position and momentum, A depends on position and momentum, and when we roll it back, it will include the second term, which include initial value of momentum, and Euler will give oscillatory sign. So to be universal, to start anywhere on this plane, right? To treat any possible initial conditions. And this is very doable, just will be waste of time, no new philosophical ideas. And if we carefully process it, this sine and cosine, and redo it for both position and momentum, we would arrive to the expression that we discussed at the beginning. So if we have zero momentum at beginning, it will be just cosine omega t for position. If there is some initial momentum, it will be in the opposite phase with this units factor, and then it will be like phase shifted, but still solution is general. If we have no initial position, but only momentum, momentum will also oscillate as cosine, but if it is simultaneous with both elongation and initial peak, then it will be superpositions of sines and cosines, right? So to get more regular expression, one does row by column to have it. And then we have this analysis of yes. Oh, wait. Repeat it without. So to have it. Yes. Meeting is done. Thank you much for your dedication to the class, questions and support of all these derivations, and hope to see you in the lab at 5 p.m.
Yes.
Yeah. I hope it's dark by then.
It's going to be, this is.
I love walking inside in the dark, school class, not even from class.
Yeah.
Like,
And
I'm kidding.
it will.